All right, now it's time to get into the misconceptions. I've divided them up into 7 misconceptions. There's 1 and then 3 pairs. The first misconception I want to address, and all these misconceptions are wrong, that's why I put them in quotes. First one is just the flu. It's not just the flu. This is a good tweet that has a good way of putting it. This isn't the common cold, and it isn't Ebola. It's not either of these. It's harder to tackle it because it's in the middle. And I want to talk about how it's in the middle and what that means. We have to navigate. We can't completely clamp down on it. We also can't completely take it for granted. So for example, if you just compare the fatality rates for cases that were detected, now there's lots of ups and downs about this, but no matter how you slice the data, COVID-19 is more deadly than the seasonal flu. This is an example of the age mortality rate that was, it ends up being very fatal for 60-plus-year-olds. And you see that it's only 1.1% fatal for 0 to 19-year-olds. But that 0.1% is still more than 10 times, 14 to 25 times higher than the death rate from the seasonal flu. And so it's about 10 times worse. That's an estimate. If you have to put a number on it, it's about 10 times worse than the seasonal flu. This is definitely worth mitigating factors to control. And it's scary to think about how it can get out of hand in places where you've had outbreaks like New York City, New Orleans, and recently Texas and Florida. So it's not just the flu. There's other things about how does it affect children. There's people who look at that graph that I just showed you. They say children are immune. That's not true. But there's also people who look at it and say, I'm worried about the kids. They're especially vulnerable here. Actually, they aren't. If anything about this age curve, they definitely are the least impacted age group. And not all diseases are like that. In fact, most respiratory diseases and most flus go the other way, in the sense that they have much higher age dependence. The main thing I want to say is that actually the good news in this case is that children are not hit as hard by it as those with older ages. The question is, we all know that children can catch it, and they actually have high viral loads and they do catch it. We don't know yet why they don't get as sick, and very few of them die. So there are smaller studies that looked at the infection, and they came up with rates, and they looked at it, and they looked around, and they said children are not as infective as adults. But then you got this headline. You may have seen this headline. It came out about a month ago. This is actually one of the better examples of the headline, because this says older children spread the coronavirus just as much as adults. The paper itself actually says that they spread the coronavirus more than adults. But even within the uncertainty bars, you can't say that. They overlap. This is at least a conservative report of what the study's own issue was. But this seemed weird to me when it came out, because I had been looking at all these smaller studies that said children are about half as infective as adults. And then this big study comes out. Usually bigger means better. But then I was noticing on Twitter that there were some people that were looking at this, and this is an accurate reflection of what the disease, what the article about the disease says. This is the article, and they say, we show that the household transmission of the virus was high if the index patient was 10 to 19. And that just didn't go with what other people saw. There was a flaw in the study, and that is what caused the 10 to 19 age range to be artificially inflated. This was pointed out on Twitter, which gives me a little bit more confidence in Twitter, as soon as it happened, but it took another month for it to be rigorously analyzed. Overlapping set of data, they went back and they looked at it, and the problem is, if there was simultaneous infection, you know how in baseball the tie goes to the runner. Here, simultaneous infection, they gave the tie to the child. But you really can't do that. You don't know who was infected first. In fact, they were probably infected at the same time. And so you can't say anything about the child transmitted it to other people. This later study, looking at same pool of data, found only one clear case of an index case in the 10 to 19-year-old range, and that was a 16-year-old who transmitted it to his sister and did not transmit it to either of their 50-year-old-ish parents. So the data, when you actually look at it, seems to say the same kind of things, that there is lower transmission rate from the children. And they said that in this new study, the rate from children to household members was low in this setting where everyone was distancing, quarantining, isolating, and afraid of the virus. But that's all that the study ever said. So that one data point got in the headline, and that one data point turned out to be inaccurate, or an inaccurate interpretation of the data. This has now come out, and just on Friday, and today, the reporter for it said the study had a big flaw. There's a scientist who says, I hope that scientists will stop citing this paper, because it was clear from the start the study was not designed to answer the question that was in the headline. By the way, notice that the scientist is a little bit harsher. The reporter still seems to be defending the study, and I'm just like, listen to the scientist here, honestly. Here's somebody who noticed that the original article had 400,000 shares on Facebook, and the retraction is going to have maybe 1/100th of that amount. Again, the lie goes around the world while the truth is getting its boots on, to paraphrase Mark Twain. And that happens even more quickly in an age of social media. So what is the answer? How effective are children? Well, the answer is, don't just look at one study. Look at a bunch of studies. Look at a meta-analysis. And here's a really good example of a meta-analysis that looked at all this, and let me show you what the answer is. The adult transmission to the rest of the household is around that red bar right there, and you see that the child transmission is about half the red bar. Adult transmission, overall, the transmission tends to be 15 to 20%. Adults are on the high end of that, children are on the low end, and they infect at about half the rate or less. So those are the misconceptions about children. The other one is misconceptions about masks, and again, you have either they don't matter at all, or if they would solve everything if we just did them uniformly. And again, the truth is somewhere in the middle. What I think is going to happen, and this is an opinion, that's an interpretation of the data, masks may reduce symptoms and severity more than infections. In fact, I make this argument in some of my videos that you should be selfish. You should wear a mask. Here's an example of how much an unrestricted cough goes. It goes out 3 to 6 feet. If you have a mask, you're keeping that cough in, and the virus moves not as a virus itself. It's not dry. It moves as droplets. So the mask definitely holds things in and keeps you from transmitting to others. I think there's also some evidence that it may play a role in keeping others from transmitting as much to you. People, by the way, argue that the holes in the mask are much bigger than the virus, and that's true, but they aren't necessarily bigger than the droplets. And even if the droplets are smaller than the holes in the mask, it's a little bit like a screen door with a hose that you're spraying on it. Yeah, the screen door is not going to catch everything, but it's going to slow down the hose quite a bit. That's the same kind of thing that's going to happen with viral droplets. And in fact, it looks like just reducing the virus is a good thing and has a big effect. In fact, I think that it may turn a full-blown infection into an asymptomatic infection. So masks may reduce symptoms, not infections, and the reason why they would do this is they would reduce the initial inoculum of the virus. This is the initial seed of virus that infects you, okay? And a small seed, a small amount of virus getting into you is easier to defend for your immune system than a big seed. You can think of this as you have two trees that are growing. The bad seed is going to produce a virus tree. The immune system is going to grow to respond. The immune system has the virus has more of a head start if the seed is bigger, if you have more in the initial inoculum. And so because you have this sort of arms race between the two trees in your body, if you can slow down and reduce the size of the initial seed, The virus might still infect you, but you might never know it because your immune system could take care of it before you get to it. I think that there's some anecdotes. Now again, this is hard to study because you don't want to infect people to prove a point. You have to look at real life situations and say, where did real life transmission happen? But here are 4 anecdotes right here where universal masking appeared to prevent disease transmission, or at least prevent symptoms from developing. And to me, that's great because it's the symptoms that we're worried about. Symptoms also will cause further transmission, so this should slow down the transmission and lower the R0 of the virus. All of these are cases where you had people who were all masked up, and again, this is not a meta-analysis, this is a collection of anecdotes. But I keep seeing these, and I think that they make mechanistic sense. So the last 2 misconceptions I want to talk about. This is unlike anything we've seen before, I've heard this, and we have zero immunity to this virus. Actually, neither of those are true. I'm not sure that we have a lot of immunity to this virus, but it is like something we've seen before, and we do have some level of immunity. We just don't know what the effect of it is, or if it's even significant enough to know yet. There's so much we don't know. Now, of course, the virus did not exist before 2019 in China. But there are memory immune cells from people in 2018 that can react to this virus. How could they remember? How can you have memory cells that react against a virus that didn't exist when they were made? Well, the reason is the SARS-CoV-2 virus is not the only member of its family that's in circulation. If you remember that we have the tree of infections, SARS has cousins. And remember, it has cousins who are common colds. Now, this is not an isolated finding. There are 6 different studies that I'm showing you right here that all find some level of T-cell immunity, some level of T-cells that seem to remember the virus even when they could have never have been exposed to it. So many of these are uninfected people. These are fairly high numbers, but I want to point out T-cells are only one branch of the immune system, so these are unlikely to be complete immunity, but neither are they incomplete. Neither is it nothing. It's not everything, but it's not nothing either. I have enough knots there. Remember the 3 branches of the immune system that we talked about. And we said that T cells are in the 2nd and 3rd time scale here. Remember that T cells don't prevent initial infections, but they do bring down the severity of the infection. They don't keep the virus from moving in, but they kick it out once it's moved in. And they hopefully kick it out before it causes too much damage. Okay? Remember that those are the yellow common cold viruses on the bottom of this screen. And the 4 of those are in circulation. Now there's other viruses that cause common cold too. But these cause about 1/3 to 1/4 of the common colds that are in circulation. So if you had a common cold, roughly speaking, there's a 1 in 4 chance that that cold was one of these coronaviruses. And the thing is, when you look at the coronavirus RNA, it's 60% identical to the SARS-CoV-2 RNA. We haven't seen it before, but we've seen its cousins. And the immune system has some cells that can learn to react. This is actually a research question that I've been talking about. I have some videos with more details, but the question is, how much could these common cold cousins be teachers of our immune system to teach them this is a bad virus, react against it, kick it out of our body? Now, the idea is that you can recognize cousins. Here's an example of me and my brother's family and my parents. And if you look at these, you might see some family resemblance among everybody except for our 2 wives. Everybody except for our 2 wives is sharing genes in this picture. And you have the cousins' faces look similar. Here's Brendan, he's mine. And this is Jonah, he's my brother's. They could be siblings. They look a lot alike. And they only share 12.5% of their DNA. The viruses that we're talking about share 60% of their RNA. And the immune system learns to recognize the shapes of the virus just like you learn to recognize the faces of the cousins. And they don't have to be completely identical. The question is, the more identical they are, the more chance of recognition you have. And so we actually went down to the molecular level, and I did a research project with my biochemistry students, where we went for two types of T cells, the two major types, and we said, how much do the common colds look like SARS? How much do they overlap? Do they have like a nose that looks similar or a chin that looks the same? And the whole thing is we break these down into the number of epitopes that the immune system can recognize for SARS. And this is all computer predictions, but they're fairly accurate, and they've been borne out by many experiments. There are 793 of one type of T cell epitope that can be recognized by the immune system for SARS-CoV-2. Out of those, 35% can be found similar in one of the 4 common cold viruses. In fact, 52 of the 793 can be found in all 4. This means if you saw one of those cold viruses, you have a substantial chance of having some T cells that react to SARS-CoV-2. This is one branch of T cells. This is another branch of T cells, and you see that their proportion is about the same. You have more epitopes being detected, a bigger circle, but you also have a smaller percentage, but it's still substantial, of 24% of the epitopes overlap. That means the shapes of the SARS-CoV-2 could be recognized by an immune system that had only seen the common cold before. This is the likely mechanism for why people can have a memory of SARS-CoV-2 when the T cells were made before SARS-CoV-2 ever made the jump to humans. So those are the misconceptions, and I went to see how long that was. Another 15 minutes. Not too bad.